The structures everyone sees but no one could walk through any European or American city built before 1920, and you will notice something peculiar if you know where to look. Ornate metal towers rising from rooftops, symmetrical spires, unusual radial metal frameworks, ceramic components that seem oddly out of place on buildings meant for living or work. Tour guides usually offer a simple explanation: decorative Victorian architecture or lightning rods. Sounds reasonable. Most people accept it without question and move on. But that explanation begins to unravel the moment you look closer. These structures appear with remarkable consistency across cities separated by oceans. They follow patterns. They are constructed using specific materials. And they appear most frequently on buildings that historically required reliable power long before municipal electrical grids were widespread: hotels, hospitals, factories, observatories, government offices. More importantly, when examined in historical records, these structures were not decorative at all. Between roughly 1870 and 1920, cities across Europe and North America installed what were officially described in engineering documents as atmospheric electricity collection systems. These were not experimental curiosities. They were functional, documented, and commercially deployed technologies designed to collect electrical potential from the atmosphere and convert it into usable energy. This wasn't fantasy. It wasn't folklore. It was engineering. At the time, the atmosphere was understood to contain a persistent electrical gradient, an invisible electric field between the ground and the upper atmosphere. Engineers realized that if they could elevate conductive structures high enough, isolate them properly, and regulate the flow, they could harvest small but continuous electrical currents. And they did. Cities didn't rely on these systems as their primary source of power. Instead, they were used to supplement energy needs, charging batteries, powering instrumentation, operating telegraphs, emergency lighting, and scientific equipment. The reason we don't hear about them today is simple: they were eventually outperformed by centralized electrical grids. And when that happened, the technology was quietly retired. But the structures were often left behind because removing them was expensive, because they weren't dangerous, and because over time, people forgot what they were for. What remains today is a landscape filled with misunderstood architecture. And if you know how to read it, the evidence is still everywhere. How to identify a real atmospheric power to understand what these structures were, we need to know how to distinguish them from ordinary lightning rods. A traditional lightning rod is simple by design: a single vertical metal rod, a direct conductive path to ground, no insulation, no complexity, and no horizontal structure. Its only purpose is to safely discharge lightning strikes. Atmospheric collection systems are fundamentally different. They exhibit 6 clear physical characteristics, all visible with the naked eye. First, radial geometry. Instead of a single rod, atmospheric towers use multiple metal arms radiating from a central point. These often form symmetrical, wheel-like or umbrella-shaped patterns. This increases surface area for interaction with atmospheric charge. Second, ceramic insulators. You'll often see white or brown ceramic components separating metal sections from the building itself. These insulators prevent electrical leakage. Lightning rods do not require this because their purpose is to discharge energy, not retain it. Third, horizontal elements. Lightning rods are vertical. Atmospheric collectors are not. They include horizontal arms or domed structures designed to intercept electrical potential across a wider field. Fourth, oversized construction. A lightning rod rarely exceeds a few feet. Atmospheric towers often rise 10 to 15 meters above the roofline. That scale only makes sense if height increases performance, which it does when collecting atmospheric charge. Fifth, internal wiring paths. Instead of a single cable running down the exterior of the building, these systems route thick conductors inward, toward internal equipment rooms. That alone disproves the lightning rod explanation. Sixth, multiple installations. Buildings using atmospheric systems often had several towers installed symmetrically across the roof. Lightning protection typically requires only one. Once you know these markers, you begin seeing them everywhere. On hospitals, on old hotels, on factories, on observatories, on government buildings. They were never decorative. They were infrastructure. Documented examples. You can still visit why. This is where the story becomes undeniable, because the evidence is not theoretical. It's physical, archived, and verifiable. Belmont Hotel, Massachusetts, 1891. The Belmont Hotel still has 5 rooftop collectors aligned along its roofline. Each includes copper radial arms and ceramic insulation. Municipal construction records explicitly list an atmospheric collection system, installed during original construction. You can still see it today. Pemberton Textile Mill, Lawrence, Massachusetts, 1887, 3 large rooftop collectors with 12 radial conductors each. Original blueprints archived in the Smithsonian list the system as a supplemental electrical supply. The mill ran night operations partially supported by stored atmospheric charge. Lick Observatory, California, built in 1888. 6 rooftop collectors wired directly to instrument rooms, not to lighting. Director James Lick's personal journals mention the installation of an atmospheric potential system to stabilize sensitive equipment. Michigan State Capitol, Lansing, installed in 1879. 4 large collectors at roof corners. Basement records show an electrical storage room, used until 1903. The room still exists. The equipment does not. Boston, Parker House District City Council minutes from 1885 approved installation of atmospheric poles for telephone exchange support. 3 of those poles still exist, mislabeled today as decorative historical fixtures. These are not isolated cases. Engineering journals from the era list dozens of cities using similar systems. Boston, a Chicago, a Philadelphia, Hartford, Detroit, a London, a Munich. The evidence is not hidden. It's just ignored. Why the technology DISAP prior to the disappearance of atmospheric power was not a conspiracy. It was economics. These systems worked, but they had limitations. First, low output. They produced watts, not kilowatts. Enough for lighting and instruments, not motors or heating. Second, variability. Power output changed with humidity, altitude, and weather. Storms increased output. Clear skies reduced it. Third, maintenance. Ceramic insulators cracked. Metal corroded. Batteries required upkeep. Skilled technicians were necessary. Fourth, urban expansion. As cities grew, rooftop space became valuable. Atmospheric collectors took up space without scaling well. Fifth, the rise of centralized grids. By 1910, electrical grids offered cheap, constant power. The cost per kilowatt-hour dropped rapidly. Once grid electricity became reliable and cheap, atmospheric systems lost their advantage. They weren't banned. They weren't suppressed. They simply became obsolete. And when something becomes obsolete, society forgets it existed. How history erased the MMO, where the disappearance followed a clear pattern. New installations stopped. Existing systems were disconnected. Valuable components were removed. Remaining structures were reclassified. Engineering textbooks omitted them. Knowledge died with the engineers. By the 1920s, atmospheric electricity had vanished from curricula. By the 1950s, it was no longer mentioned in history books. By the modern era, people assumed the structures were decorative. Yet the physical evidence remained. This happens often in technological history. When a system loses relevance, its story fades, even if its physical remains do not. Why this matters today. This story is not about nostalgia. It's about understanding how technology actually evolves. Atmospheric power systems teach us that innovation is not linear, that viable technologies can be forgotten, that infrastructure can outlive memory, that economic forces shape history more than invention, that physical evidence often contradicts simplified narratives. Modern engineers are once again exploring ambient energy harvesting, distributed microgrids to passive power systems, low-energy sensors, environmental energy capture. Many of these ideas echo 19th century systems, often unknowingly. The past didn't fail. It was simply replaced. And the structures still standing on old rooftops are not curiosities. They are reminders that progress is not always a straight line, that knowledge can be lost, that cities are archives, and that sometimes the most important history is hiding in plain sight, above our heads. If you've ever walked past one of these towers without noticing it, now you'll never see them the same way again. And once you learn how to look, the city starts telling its real story.